talking about projective algebraic sets. Zero sets polynomials in projective space, and the last thing we had been looking at was the Zariski topology on Pn. So this is a topology whose closed sets are the projective algebraic sets on Pn. Closed sets are projective algebraic sets. And if we had seen that form indeed a topology on Pn, and if X in Pn is a subset, give it the induced topology. Okay, so now we want to proceed with kind of doing the analogous things that we did for fine algebraic sets. So we want to talk about irreducible components. So the first thing that we notice is that projective space, and therefore also projective algebraic sets, are Noetherian topological spaces. So mark N is a Noetherian topological space. As you recall, this means that every descending chain of closed subsets becomes stationary. And we know that any subspace of a Noetherian topological space is Noetherian, so thus subspace of Pn. In particular, every projective algebraic set is Noetherian. So we only have to see that Pn itself is Noetherian. So if I have a descending chain of closed subset, projective algebraic sets, then I can look at the corresponding ideals. So then Ix1 contained in Ix2 and ascending chain of ideals. In the polynomial ring Kx0 to Xn. So thus, as this polynomial ring is Noetherian, it becomes stationary. So that means, so as you know, that means that after a certain n, we have that all the ideals become the same. Then it follows that also the chain of the closed subsets becomes stationary, because the zero set of the ideal for closed subset is the closed subset itself. So thus chain X1 becomes stationary. Because we know that we had seen that the zero set of the ideal of a projective algebraic set is that itself, that projective algebraic set. So therefore, if these after a while are the same, then obviously the sets are the same too. Okay, so that was easy. And so now we can directly apply the result we proved when we proved components before. So we get, corollary set maybe every, say, projective algebraic set has a decomposition. There's nothing to prove here because we know that every Noetherian topological space has such a decomposition. I don't remember whether I introduced the word quasi-projective, so if open subset of a projective algebraic set called quasi-projective algebraic set. And then will be particularly interested in irreducible projective and quasi-projective algebraic sets. So irreducible projective algebraic set is called projective variety. And an irreducible quasi-projective algebraic set is called a quasi-projective variety. And often I will also just say variety. There is a more general notion of variety, but that is as general as we consider varieties. So for instance, if we identify, AN with U0 in N, then we see that AN is a quasi-projective variety. At least it's a quasi-projective set, but we'll see in a moment that it's also irreducible. I mean, we know it's irreducible. And every fine variety will then also be a quasi-projective variety. Because it would be a closed subset of this open subset U0 in Pn. Okay, let me see where I am. So you remember how we did it in the fine case. We had done all these things, and then the next step was the Hilbert-Nullstellensatz. And so as a last thing about projective varieties in this section, we want to prove a projective version of the Nullstellensatz. Say precisely what is the relation between homogeneous ideals and their projective zero sets. In particular, maybe what is the condition for the zero set of an ideal in empty set. The statement will be very similar to the fine case, but in the fine case the proof was quite difficult. In particular, we didn't prove the weak version, we only deduced the strong version from the weak version, but that was also not easy. Here it's quite easy because we can reduce the projective version of the Nullstellensatz to the affine version. And this we do, so reduce. First I can say, well, so we want to, so this is analog. So the affine case, we will prove it by reducing to the affine case done using cones. So the idea is very simple. If you have a projective variety in Pn, it's the zero set of some ideal in kx0 to xn in projective space. Now, if you take the zero set of the same ideal, now however in an plus 1, so where you don't don't look at projective space but the corresponding affine space, then this will be a cone. And applying the usual Nullstellensatz to that will translate into a projective version of the Nullstellensatz for these projective varieties. So let me first talk about these cones. So, non-empty affine algebraic set x in n plus 1, which I will give the coordinates x0 to xn, is called a cone. If for all p, a point with coordinates a0 to an, in x, also all multiples of this point as a vector lie in x. So I could call this lambda times p, by which I just mean the point with coordinates lambda a0 until lambda an, with lambda and k, are elements satisfy lambda p in x. You have to think, so somehow here you have the origin, and for every point that the thing contains, it contains the whole line through the origin. So it somehow has some kind of form. I mean, obviously the origin, so also these lines, contrary to how it looks like, all go through one point. And so you see this thing is like this, but by lines. Okay. So that's a cone. And how to get cone out of a projective variety? So for x in Pn, projective algebraic set, we find cone over x so I denoted x, just say I could say it's the set of all points a0 to n 1 such that if I take the equivalence class, it lies in x. And to be a cone, it has to contain the whole line through any given point, so it certainly has to contain the origin, so we add to it origin of a n plus 1. So you can see that this is a cone because equivalence class here is all multiple, two things are equivalent if they differ by multiplying by a non-zero constant. Then in addition to contain the whole line, you have to also allow this constant to be 0, then you get this. And so altogether, this satisfies the property that it is a cone. So and now, this is useful for us because, as I said, the ideals of x in n and the cone of x in the n plus 1 are related. So you can, so I have the following. Lemma. Okay. First, let x n, so non-empty projective algebraic set. Then, if I look at the ideal of the cone of x, so this is, so to speak, the ideal in the affine, so in one, the non-homogeneous ideal in so the ideal of the cone of x as a closed subset of a n plus 1 is equal to the homogeneous ideal of x. And the second statement is so assume, so let x equal to the projective zero set some ideal a homogeneous ideal then the cone of x is equal to the zero set in a fine space of the same ideal, possibly union origin. And in fact, and of x is equal to I if x is not empty. So you have to add 0 when only when x is empty. So in some sense, so this is basically a reformulation of the statement that I had before, that the last time, that you can say that you can also define the zero set of an ideal as the set of all points in Pn, so that for every representative of that point, so that every polynomial in the ideal. So let me try to. So we had this result. Mark that things that we can also say zero set of a homogeneous ideal equal to the set all n such that f of a0 to an is equal to 0 for all f in I and all representatives. A0 to an of P. No, we had originally defined the zero set as being the common zero set of the homogeneous elements in the ideal, but one can also equivalently define it like that. And a similar statement we had for the ideal of a projective algebraic set. Also had that the ideal of x was the set of all f in polynomials. You don't need to require them to be homogeneous, such that again f of p is equal to 0, f of a0 to an for all representatives of P. So if we, with that, this basically becomes an exercise. Maybe I will just do one of the, so the proof of the lemma is essentially an exercise, but I can do one of the 2 points. Which one did I want to do? Yeah, I want to do first. So what is, if I take the homogeneous ideal of our x, so this by definition is what I just wrote. So the set of all f in K such that f of A0 0 for all p x and all representatives but but what does it mean? The representatives are just all the multiples. So by definition, this is the same. This just means in a fine space, this just means you have any representatives and then all multiples of it. So this is the same as the ideal of the cone of x minus 0. No, because the points taken here are precisely the cone of x minus 0. And if x is not empty, then you can see it contains for every point, this cone will consider, so what we have here, the cone of x minus 0 will be a line through the origin without the origin. So it contains such a line, and possibly, and so in the moment the origin 0 is missing, but we know that the the ideal of a subset is the same as the ideal of the closure of the subset, and so when we take the closure, we add, so we can add 0 to it. This is x if x is not empty. So, and 2 I leave as exercise. Okay, and so with this, now we can go and prove the projective version of the Nullstellensatz. As I said, was very simple. A very simple, very analogous to the affine case. First, so it's this theorem, projective Nullstellensatz. So we take an ideal in K x0 to xn, a homogeneous ideal. And now the first statement is the analog of the weak Nullstellensatz. So the 0 set of this ideal in projective space is empty. So in the affine case, the statement would be that if the ideal is equal to the whole of kx0 to xn, this is not quite true. The statement is if and only if E contains all monomials of n in x0 to xn for some positive n. So the zero set is empty if, and so if it contains all monomials of degree n, then by, as it's an ideal, it also means it contains all monomials of degree bigger than n. So it might not necessarily be the whole of the polynomial ring, but it contains all homogeneous polynomial of sufficiently high degrees. And the second statement is, however, if we exclude the empty set, then the strong Nullstellensatz is the same as before. So if the zero set of the ideal, now obviously, I don't know why I wrote different, so I meant is equal to empty, no? That was the point. It's empty in the affine case if and only if it contains the whole polynomial ring. Here we don't quite have that, but it contains all polynomials, all homogeneous polynomials of a sufficiently large degree. Now, if it's not empty, then we have the same statement as is in the affine case. Then if I take the homogeneous ideal of the zero set of this ideal, then this is the radical of I. Okay. We have a slightly different version of the weak Nullstellensatz and an identical version of the strong Nullstellensatz, as long as we exclude the empty set as the zero set. So, and now how does one prove that? As I said, we want to...
Professor?
Yes?
In the first statement, I think it's true in n equals to 0, because n equals to 0, then f is just constant polynomial. And
yeah, I can also write n, yeah, that's true. I can also write n bigger equal to 0. But, I don't know before what n is. No, it could be that it turns out that for I, this n is 100,000, but it's still, but it, in some cases, obviously if n is equal to 0, then we would have that, that I is equal to the whole polynomial ring.
yes.
But that obviously I don't want to exclude. That can also happen. But the way I said it, as I said it, it was also correct. It was only, because, if it contains everything for all n bigger than 5, it also contains everything for n bigger equal to 5, it also contains everything for n bigger than 5. But yeah, but it is maybe, I can write it like this, then it's more complete. Okay, so let's now do the proof. So I write X for this zero set. First, let me look at the case. So we just want to prove the two things. First, I prove one. So I assume that if X is the empty set, then this is obviously equivalent to the statement that the cone over X is 0. Because by definition, the cone is always taken by, adding 0 to the corresponding equivalence classes. And so we have this. And by what I have just stated here, this number 2, it follows that so the, so put it, zero set of I either equal to the empty set or the zero set of I is equal to 0. I know that the zero set of I union 0 is the empty set. Is equal to 0. So the thing is the zero set itself was either empty or 0. So now I can apply the Nullstellensatz, so the affine Nullstellensatz by Hilbert Nullstellensatz. This is equivalent to that, so I have the radical of I equal to the ideal of the cone of X. And so this then must contain, so the ideal of the point 0 is the ideal generated by x0 to xn. And the idea of the empty set would be the whole kx1 to k x0 to xn. So at least this ideal of C of x contains this. And so, and that is the proof of 1, basically, because thus for all say I, there exists a j I with xi to the ji is in the ideal of the cone of x, ideal of the cone of x. Because this is the power of an element here. And so we take n to be the sum of all these numbers, 0 plus an, then so I made a mistake. Sorry. I mean, I didn't make a mistake, but I said something. So let's go back here. So we have the radical of I contains this ideal. So that means that it must contain, for every element here, it will contain a power of that element. So therefore, for all I, there is an ji such that this ji'th power of xi is in I. No, because xi itself lies in the radical, so this power lies in I. And now I put n equal to the sum of these numbers, then I contains all monomials of degree n, 0 to xn. Okay, so this was quite simple, and the second one is even simpler because we don't even have to bother with the 0. Is it? So let that x, which was the 0 set I, is not empty. Then we have seen by the remark, the lemma I wrote there, that the homogeneous ideal x is the ideal of of the cone of X. The cone of X is the ideal of the affine zero set I, because we had seen that the cone of X is this. And by the Nullstellensatz, the ideal of the zero set of I in the affine case is the radical of I. And that proves it. So by a affine Nullstellensatz. Okay, so this was quite simple. So as you can see, everything is very similar to the affine case. One has this strange, so you have, for instance, a 1-1. You also have again a 1-1 correspondence of the closed, of the radical ideals in kx0 to xn, the homogeneous radical ideals in kx0 to xn, and the projective algebraic sets, as long as you exclude this one here, which corresponds to, and so therefore this is sometimes called this ideal is sometimes called the irrelevant ideal. So, because it doesn't correspond to a closed subset of Pn. So x0 to n is called relevant ideal. So we have a 1-1 correspondence, so we have a bijection, so 1-1 correspondence. Projective algebraic sets Pn, X in Pn, and I could say so we'll call it non-irrelevant radical ideals. In kx0 to xn, which, so x is sent to the homogeneous ideal of x, and so I forgot, obviously, non-irrelevant homogeneous radical ideals. So only use homogeneous ideals. And a homogeneous ideal is sent to its projective zero set. And here, non-irrelevant means I take all homogeneous radical ideals with the exception of this one. So every homogeneous radical ideal corresponds by 1-1 corresponds to a projective algebraic set, except that one has to leave this one out. Okay. Now, as a remark afterwards, I also want again to say that projective algebraic set is irreducible if and only if its homogeneous ideal is a prime ideal. And the proof is basically the same as in the affine case, or rather well, not quite. I mean, in the easy system, again using cones. So let me just say corollary. I mean, there are two directions. So anyway, so a projective algebraic set x in n is if and only if homogeneous ideal of x is a prime ideal. And and the second statement was that if f is a homogeneous irreducible polynomial, so if f in n irreducible is then the zero set of f so part 2 follows from part 1 in exactly the same way as in the affine case. If f is irreducible, then it will generate a prime ideal, and therefore part 1 applies. But also conversely, it's easy to see. But now let's look at part 1. So there are two conclusions, so two directions. So hope that's the right direction. So assume x is irreducible. No, I assume that x is reducible. Right. Assume x is reducible, then we can write x is equal to x1 union x2, where x1 and x2 are two closed subsets. So where both of them, x1 and x2, are closed subsets in X, but none of them is equal to X. So then it follows that if I take the cone over X, I can write this as the cone over X1 union the cone over X2. And I mean, the cone over X1 is the zero set of the same as ideal as X1 is the zero set of, only in the affine space, so it's also closed, and none of them is equal to the cone of X. So with C of Xi closed, so it follows that this cone is reducible. And from this it follows that the ideal of the cone of X is not prime. But we know that this is equal to the homogeneous ideal of X. Okay, so that's one direction. Now for the other. In some sense, one does, for the other direction, one does the same proof as in the affine case. There's only a little bit, one has to just work a tiny little bit, because one can only work with homogeneous polynomials. So assume that, so let I, which is X, not be prime, not a prime ideal. So that means exists polynomials f and g in I, which are not in I, none of them is in I, with f times g is in I. So, okay, so that's basically, in the affine case, then we took the zero, x intersected zero set of f and x intersected the zero set of g, and then this was a decomposition into closed subsets. We want to do the same, but f and g are not homogeneous, so it's a bit more complicated. So we have to first reduce to the homogeneous case. So we choose I and j minimal such that the homogeneous component of degree I of f and the homogeneous component of g of degree j are not in I. So we can, if we want, if we subtract from f homogeneous components of lower degree, they will lie in I, and nothing changes, the same here. So we can assume that these are the lowest degree homogeneous components of f and g. So by subtracting lower degree homogeneous components f and g, we can assume that phi and j are lowest degrees homogeneous components f and g. Okay. So, but we know that our ideal is a homogeneous ideal. So therefore, let me first one more step. So thus, if I take fi times gj, this is the lowest degree homogeneous component of f times g. But as our ideal is a homogeneous ideal, it contains with every element all its homogeneous components. So it follows as f times g lies in I, it also fi times gj lies in I. So which just means that we could have assumed from the very beginning that f and g were homogeneous. And then the argument is the same as in the affine case. Where is it? So we put x1 equal to set I union f I the zero set of I union j. Then, as in the affine case, we find that x1 and x, so that both xi are subsets of closed subsets of x which are not equal to x. And if I take x1 union x2 to x, so it follows that x is reducible. Okay, so much for this. This, for the moment, finishes this chapter on projective varieties and projective algebraic sets. Maybe the next exercise give you some homework so that you can study a few more examples of that, because I didn't have so many examples in the course. Now I want to come to the next chapter, which is about morphisms, functions and morphisms. So whenever you basically study anything at all, you always are interested in the maps between the objects which are compatible with your structure. So you can do linear algebra, so you have vector spaces, and then in some sense the interesting thing about vector spaces are the linear maps, which are the maps between vector spaces which are compatible with the structure. In differential geometry, you study differentiable maps between differentiable manifolds. Talk about groups and rings, you talk about homomorphisms of them. And for varieties, the maps which will be compatible with the structure will be called morphisms. And special case of morphisms are the morphisms to K, which play a role to understand the other ones. But in some sense, really the main tool to understand anything is in terms of morphisms. So, so we study maps. Phi x to y of varieties which are compatible with the structure. So I will first maybe let me look at the special case, which is a bit easier before I make the general definitions, which are the polynomial maps of affine varieties or affine algebraic sets. Okay, this is a kind of general, will be a bit more general, but so so a polynomial map will just be a map. So this is a map. So we have x subset En, y subset Am, and so this will be a map from x to y such that the coordinates of the maps, so the m coordinates of the maps, are given by polynomials in x1 to xn. So let me write this down properly. So let x n y in M be affine algebraic sets. Map of the form just I write it f1 fm from x to y. So a point P is sent to what one gets when one puts the coordinates of P into F. So 1 of P of P for Fi some polynomials. So you just put the coordinates of a point in X into a polynomial. This gives you m different polynomials. This gives you a point in AM. And we require, obviously, when we want a map from a morphism from a polynomial map from X to Y, that this lends you in Y. So such a map is called a polynomial map. From X to Y. Okay. So this is, in some sense, the simplest way how one can think of, after all, the algebraic geometry is somehow about zero sets of polynomials, so it seems very natural to say that the maps between such sets should also be given coordinate-wise by polynomials. So say a bijective polynomial map inverse is also polynomial map called an isomorphism. Okay. In which case we say that X and Y are isomorphic. Y are isomorphic. That's this definition. I should maybe, yeah. I do have actually this change. So the first thing, so I make a couple of remarks. Remember, we had defined the coordinate ring Ax was the polynomial ring. So if X is in An, k x1 to xn, divided by the ideal of X. And we could also identify this with the so-called polynomial maps. So this is equal and naturally identified with polynomial functions, not maps, polynomial functions. On X, and by this is just meant the set of all functions that you obtain by taking f restricted to X, where f is a polynomial. Okay, these are naturally identified because obviously the map which sends a polynomial to its restriction to X is a surjective ring homomorphism whose kernel is the ideal of X. And so now such a polynomial map obviously will be determined by the restriction of the Fi to X. So I can as well say that instead of being given by an n tuple of polynomials, it's given by an n tuple of polynomial functions. So on M X Y depends only on the I restricted X. So thus also say that a polynomial map is given by an n tuple of polynomial functions. By tuple polynomial functions. Okay, this is obvious, but just I would use that notation whenever I find it useful. So we just give a few examples of polynomial maps. Could, for instance, look at this conic or parabola if you want to see y minus x squared. So the real points would look like that, but obviously if you're of an algebraically closed field, it might be different. And so we can have a morphism, say, from A1 to C, which sends, so I can write, if I call the coordinate on A1 t, it would be the morphism t squared. This obviously, sends A1 to the zero set here is a morphism, and it's a polynomial map. Inverse is just the projection to the first factor. That means if I have a point A comma B, it is sent to A. And you can see, you can easily check these are inverse, so that means thus isomorphic to A1. So I write this, I use this notation, isomorphic. Now look at some very similar case. So let's instead look at C, which is the zero set. And so instead we can look at the zero set of, say, y squared minus x to the 3. So this was in A2, also in A2. We again can find there's an obvious map from A1 to this thing, no, because I can view x as the third, y as the third power of something and x as the second power. So you can take t squared to the third from A1. So for the C2. So C2 is a polynomial map. And it's quite immediate that this map is surjective. And in fact, bijective. But it's not an isomorphism. In fact, I can write down the inverse map. So the inverse, call this map also phi. Inverse phi to the minus 1. What does it do? So how does one get t when one so if one knows a to the third and a squared, one gets a by dividing one by the other. So the inverse is given by is a map from C to A1, which sends a point AB on C2. So divided by A. But this makes sense whenever A is not 0. And if you look at the way the map goes, 0, the point 0 here is mapped to 0, 0, and that's the only thing. So if A is equal to 0, then so the only point of this curve for which A is 0 is that also B is 0, and so 0 when and then also so, and you can see that this map is not given by a polynomial in A and B. So you cannot write this as a polynomial in X and Y. So this is, so the inverse is therefore not a polynomial map. Not a polynomial map. In fact, it's not difficult. I mean, later we will see that in fact A1 and C2 are not isomorphic. And in some sense, if one makes a picture, for instance, over the real numbers, one can see it quite easily because the curve will somehow, I don't want it, the curve will somehow look like this. Here is 0. And so somehow, you can, it somehow does not look very much like a line. Here, it's curved like this, but somehow it's still similar to a line. But here, obviously, something happens, which later we will see that this thing has a singularity at the origin. Yeah, I should maybe also, I don't know what the number in here is. This was 1. Maybe I just want to generally mention that, so the polynomial maps just from X to A1, by definition, are just the polynomial functions. If you look at the definition, it's just that. Okay, so this was this example. So now we'll see in a moment that so next time we will study more general morphisms, and which are not just polynomial maps. And then a very important thing to study is what one calls the pullback. So if you have say a polynomial function on the target, then you can take the composition with the morphism, and this will again give you a polynomial function on the source, and this contains all the information about the original. If you know these, you know all the information about the original polynomial map. So let me write this properly and also explain it more properly. So pullback, polynomial functions by polynomial maps. So so I first have to define it. So if I have again two affine algebraic sets, so let X in AN, Y in AM affine algebraic sets. And assume we have a polynomial map between them. So let phi from X to Y, so phi, which I can write as F1 to Fm, the Fi are polynomials, from X to Y, the polynomial map. So now assume I have a so then pullback from AY to X by so the pullback of some polynomial function on Y is just defined to be the H composed is a homomorphism. Maybe I have to make it explicit. So first I have to see Y. If I start with a polynomial function on Y, I get a polynomial function in X. So note that so I can write, so if H is equal to H restricted to Y for H polynomial variables corresponding affine space in which Y lives, then how do I do the composition? The composition is just, the map was coordinate-wise given by these polynomials. So that means the composition is just, we put the Fi instead of of the variables. So then H composed with phi just equal, so we take H, put into it F1 to Fm instead of the variables, because the ith coordinate of the image point is just this. And this is, however, but this is now, here we had to restrict it to y, so we view it just as a function on x. So this gives me this. And clearly, if I put some polynomials into a polynomial, I get a polynomial. And so this is a polynomial restricted to x. So we have h of f1 to fm, polynomial f1 to xn obtained by replacing yi by fi, f1 to xn, and then, therefore, this is a polynomial, and you have a polynomial restricted to x, so this is clearly in ax. And from the definition, it's also clear that it's a ring homomorphism, because if I take here the sum of two functions in a y, this corresponds to taking the sum of these polynomials, and I get the sum here, and the same for the product. Okay, so this is this. Now, so the interesting thing here is that these two things determine each other. So if I have a polynomial map from x to y, I get a ring homomorphism from, or a k-algebra homomorphism from the other around, from ay to ax. And conversely, we will find that if any such homomorphism from ay to ax will give us also a polynomial map from x to y. So, yeah. So phi determine each other. Obviously, clearly, if I know phi, I can pull back by it, but I claim I can also get back star. And the statement is as follows. So theorem that x and y be affine algebraic sets. So the map so we look at here the polynomial maps phi from x to y to the k-algebra homomorphisms from ay to ax. Which is given by pullback, so phi is then to phi star bijection. Okay. So now basically, let me see. So I can maybe, so it's clear that I've already told you that if I take the pullback via polynomial map, this is such a K-algebra homomorphism. So X to Y polynomial map, have that phi star Y is, by the way I constructed it, now I want to construct the inverse map. Map phi star. So to a K-algebra homomorphism, I want to associate a polynomial map. And that's actually quite simple if you think of it. So if you look at the definition here, so the pullback is obtained by putting the coordinates of the polynomial map into the polynomial which defines the polynomial function. So if I instead just take here the ith coordinate on y, so then the pullback of that is just fi. And so if I just look at the pullbacks of the coordinates, these will give me the coordinates of the polynomial map. And so we can just use this as a definition and see that it works. So let y1 go ym. So we assume y lies in some am, and let these y1 to ym be the restrictions of the coordinates to y. The elements in y, the restrictions of the coordinates. So we put fi to be okay. So let me see. I can leave that, but now, so I want to give the inverse map, so I have to start with the K-algebra homomorphism and get polynomial map. So let P from AY to AX be K-algebra homomorphism. By what I just said, it seems to be a good idea to put, to look at the pull. So if this phi is the pullback homomorphism of a polynomial map, then the coordinates of the map are the pullbacks of these yi's. So that means I should apply phi to yi. So put fi to be the phi of yi. So these are some definitions, some elements in AX. And now we let I call it maybe, what notation do I want? Say index phi, the polynomial map, which now I write in terms of polynomial functions, so f1, so fm. So this a priori, so these are some polynomial functions, so this gives me a map from x to am a priori. I would like that this gives me a polynomial map from x to y, but I have to see, therefore, that x is mapped into y. Polynomial map. We have to see if I take this psi phi of x lies in y, then it's a map to y. So therefore, let H be a polynomial which lies in the ideal of y, vanishes on y. I have to see that it vanishes on the whole of the image. Okay. Then it will be done. So what do we do? If we take H composed with phi by what we just had, this is H of F1 to Fm. So this is H of phi of y1 of m. Now, phi is a homomorphism of K algebras. So that means I can pull it out of a polynomial. No, I can pull it out of a sum of multiplying by constants and out of products. So this is equal to phi of h of y1 to ym. But yi is just the coordinate of am restricted to y. And so h of y1 to ym is just h restricted to y. But h restricted to y is 0, because h lies in the ideal of y. And phi is a homomorphism, so this is 0. And so this shows that indeed this gives a map from x to y. X to y is a polynomial map. Okay. So the final thing is that we have to show these two things are inverse to each other. So I have shown I have one map here, and now I have this map backwards, which sends phi to this thing which I called phi psi index phi. And so we have to show that phi maps to phi star and large phi maps to psi inverse. I will only choose, check one composition, which is the easy one. The other one is not much more difficult, but I think I have kept you long enough. So we know if P is equal to F1 to M from X to Y with Fe. If this is a polynomial map, then with Fe in X, then then we have that if I take the pullback via phi of the ith coordinate, this is Fi. So thus, if I take this, what I call psi of phi star, we have this homomorphism associated to, so now I've composed them in this way. This is, what does it do? It takes, according to our definition, it is the map which is given by the pullbacks of the yi's. So this is therefore just equal to F1 to Fm, which is phi. So this composition is the identity. The other I leave as exercise. Okay, maybe I stop here. I'm sorry I went so much over time, but I thought it would be good to bring this to a reasonable close. So are there questions? Or comments? Otherwise, I wish you a good weekend and also nice holidays. I mean, it's not immediately, but at least we won't see each other before then. And
Thank you.
And I think you will also have your first tutorial tomorrow, no?
Yes,
Okay.
yes.
Okay. So have a nice evening then.
Thank you.
Okay. Bye-bye.
Thank you.
Bye.
Thank you very much.
Mm-hmm.